There's something that's been bothering me in a wonderful kind of way about this whole Mars business. Everyone talks about it like it's just a matter of building a bigger rocket. Like the problem is, engineering. Get the thrust right, get the fuel right, point the thing in the right direction, and off you go. Simple as that. But wait, let me back up a second. I was sitting in my office once going over some calculations, and I started thinking about what it would actually mean for a human being. A real living person with bones and blood and a nervous system that evolved on this planet, to spend 6, 7, 8 months just getting to Mars. And I don't think most people have really sat with that. I mean, really sat with it. So let me try to explain what I mean. Here's the thing about your body. It doesn't know it's in a rocket ship. Your body doesn't read the mission briefing. What it knows is whether gravity is pulling on it or not. And when gravity stops pulling, when you're just floating there in a tin can between here and Mars, your body gets very confused very quickly. Your bones, you see, they're like, imagine a bridge that has cars driving over it every day. The constant load, the constant pressure, that's what keeps the bridge strong. Keeps it from rusting out in certain places. Your bones are the same thing. They respond to stress. They need stress. And in zero gravity, there is no stress. So your bones just start dissolving. Actually dissolving. Calcium just leaches out into your blood, into your urine, gone. Now I find that kind of curious because we think of bones as this permanent hard thing inside us, like scaffolding. But they're not, they're alive. They're constantly being broken down and rebuilt. And they only get rebuilt if you're using them, if you're pushing against something. And in space, you're not pushing against anything. And that's just the bones. Then there's your heart. Your heart is a muscle that evolved to pump blood upward against gravity up to your brain. In space, the blood just floats. It goes everywhere. Your face puffs up. Your sinuses fill. Astronauts describe it as feeling like you have a permanent head cold for months. And the heart, because it doesn't need to work as hard anymore, it starts to shrink. The muscle gets smaller. Just like any muscle you stop using. Now wait, hold on. Let me make sure you're following this. I'm not talking about some theoretical future person. I'm talking about what happens to healthy, fit, incredibly well-trained astronauts on the International Space Station right now. After 6 months in space, some of them they come back down and they can't walk. They have to be carried off the capsule. Carried. These are not weak people. These are extraordinarily strong and disciplined people. And after 6 months of floating, their legs just don't work properly anymore. And that, you see, is only the trip to Mars. 6 months each way. With nothing you can really do about it. You can exercise on resistance machines, and they do, for hours every day, and it helps some, but it doesn't stop the process. Not completely. I had a friend, a biologist, very smart fellow, and I asked him once, I said, look, what's the minimum gravitational field that a human body can tolerate long-term without serious deterioration? And he looked at me and he said, honestly, we don't know. We have never kept a human being in partial gravity long enough to find out. Mars has about 1/3 of Earth's gravity. We don't know if that's enough. We have a guess. We have a hope. We do not have data. I find that completely, utterly astonishing. We are planning to send people to a place for which we do not yet know if the destination itself is survivable long-term. Never mind the trip. Even if you get there 1/3 gravity for the rest of your life, what does that do? Nobody knows. But here's where it gets really interesting. And this is the part that stops me cold every time: radiation. Now when I say radiation, I don't mean the kind from an X-ray machine. A little zap, go home, you're fine. I mean cosmic rays. I mean high-energy particles that were shot out of exploding stars halfway across the galaxy, traveling for millions of years. And now they're coming right through the hull of your spaceship as if it isn't even there. Because to them it isn't. On Earth, we don't think about this because we have a magnetic field, this enormous invisible shield around our whole planet, deflecting these things, bending them away, and we have the atmosphere on top of that, 2 layers of protection we carry with us every second of our lives and never once think about. In space, between Earth and Mars, there is no magnetic field. There is no atmosphere. There's just you, and a few centimeters of aluminum, and the full fury of the galaxy coming at you. Now you can build shielding, and they have ideas about shielding. Water is actually quite good, because hydrogen is good at stopping certain particles. But here's the trouble. Some of the most dangerous particles, the really energetic ones, they don't stop when they hit shielding. They produce more particles, secondary radiation. You add more shielding, and you make it worse. You can add less, and it doesn't help enough. And I really can't give you a good solution here, because there isn't one yet. Not a satisfying one. And I'll be honest, this one I find the most troubling. Because the bones you can maybe fix when you get back, the heart muscle you can maybe rehabilitate. But radiation damage to your DNA, to the cells in your brain that accumulates, quietly, over months, and some of those cells, they never come back right. Now, does this mean we should give up? I mean, no, I don't think that's the right conclusion either. That's not the way I think about these things. The interesting thing to me is that every one of these problems, the bones, the muscle, the radiation, every one of them is essentially a question we don't fully know the answer to yet. And that's not a reason to stop, that's the reason to keep going. The question is whether we're being honest, really honest, about what we don't know. And from what I can see, we're sometimes a little optimistic, enthusiastically optimistic, which is fine. I mean, you need that to do impossible things. But you also need someone in the room who says, now wait a minute, let's be careful here. Let's not be in such a hurry that we miss something important. Because the most interesting frontier isn't Mars. Not quite. The most interesting frontier is the one right here, the human body, and what it will do in a universe it was never designed for. And that, when you think about it, that's the real question, isn't it? How is it that that works? I gotta stop somewhere.